In this presentation, I'm going to talk a bit about the periodic trends that exist on the periodic table. So there are a few of them that we're going to discuss, and I'll just go through them sort of one at a time and explain what they mean, and then explain what the trend is and why that trend exists. So this first one is atomic radius. The definition here, and it's important that you understand the definition of each before I describe the trend. The definition here is the distance from the center of the atom's nucleus to the outermost electron. And so what we're saying is like basically the size of the whole atom, because you're going from the nucleus, which is at the center, to the outermost electron. So in the group, this is as you're going up and down, right? A group is a column of the periodic table. So as you go down the periodic table, the radius is getting larger. The reason for this is you're adding more energy levels, all right? So if you see there, the little rings in the Bohr model represent some different energy levels that we're adding. And so we're saying like magnesium has more energy levels than beryllium, and calcium has more energy levels than magnesium, et cetera, et cetera. And so the atom is literally getting larger as you're adding more and more electrons onto the outside. So hopefully that should make sense. As you go down the periodic table, the atoms are getting larger. The period trend is a little bit more confusing, and so what's happening here is as you're going across the periodic table, things are actually getting smaller. The reason is a little complicated, but it has to do with the charge that is being felt by the outer electrons from the nucleus. And so without getting too in-depth in this, what's happening is as you're getting toward the right side of the periodic table, those ones have a greater charge that's experienced by the outer electrons. It has to do with a concept known as shielding. Basically, all of the electrons on the inside of an atom shield the outside electrons from the charge of the nucleus. But as you're going across the table, the number of shielding electrons is not increasing, but the number of electrons you have on the outside is. And so generally speaking, it's a complicated system wherein what's being felt on the outside, the portion of the nuclear charge, that is the portion of the charge from the protons in the nucleus that's being felt on the outside is getting larger as you're going to the right. And so as these are feeling a larger and larger charge coming from the nucleus, the electrons on the outside are getting sort of sucked in by this larger charge in the nucleus. And so that is what's happening as you go across the period, and so they get smaller as you go across the period, which seems sort of counterintuitive because you're adding more electrons on. But as you're adding more electrons on, again, you have that greater charge in the nucleus, and that greater charge in the nucleus is pulling the electrons in, and they actually get smaller as you go from left to right. This is just a general trend showing you some radii for some different things. You can see that there are some exceptions of the rules, but generally speaking, the trend is the same, okay? So as you're going down and to the left, you're getting really, really big. Okay, so a little test here looking at magnesium and calcium, trying to figure out which one's larger. So here's where magnesium and calcium are. The one that's larger is going to be on the bottom, so it's calcium. Here looking at potassium and chromium, potassium is on the left, chromium is on the right. The larger one is going to be the one on the left. Oh. So potassium in that case. All right, and then looking at chlorine and bromine. Bromine is down lower. That means it's more energy levels. All right, so bromine is larger. Actually, really quick, going back here, talking about potassium and chromium, remember that with the atomic radius, what's happening here is in the chromium atom, the electrons are feeling a greater charge coming from the nucleus, so they feel sucked in a little more as you go there. So that's why chromium is smaller and why potassium is larger. All right, the next one we're going to talk about is ionization energy. Ionization energy is the amount of energy it takes to remove an electron. So remember here, we're removing an electron from something. The group trend, generally speaking, is that as you're going down the group, the ionization energy gets smaller, and the reason that it gets smaller as you go down the group is because you're adding more and more energy levels on, and so as you go down a group, the electrons are on the outside of the atom. They're on like really far away from the nucleus, and so it's easier to pull the electrons away. So that is mostly what's happening there, is the electrons on the outside are really easier to take apart. And then for the period, what's happening here is that as you have, as you're moving from left to right, they're getting closer to being like noble gases. And so there's this thing called the octet rule, which says that atoms want 8 valence electrons so that they can be like a noble gas. And actually, I'm going to jump to a later part in this PowerPoint presentation in just a second here to explain that to you. But because the atoms are closer to being like noble gases, they want to give up their electrons less. And so, as I said, I'll just actually jump to that part of the presentation right now. So we'll skip through all this for just a second and talk about valence electrons for a second. So when we say valence electrons, I'm talking about the outer electrons in a substance. And so if you made an electron configuration or an orbital filling diagram, the outside electrons are the ones that are in the outermost energy level. And so the energy levels, remember, if we said like 1s2, the energy level there would be 1. Or if we say 2p6, the energy level there is 2. And so we talk about these different things. And so basically, for the purposes of this class, when we talk about valence electrons, we'll only be really talking about the main group, which remember is the S block and the P block, all right? Or sometimes it's called the A group, columns 1A and 2A, and then 3A, 4A, 5A, 6A, 7A, and 8A, all right? And they follow this pattern, right? If it's in the 8th column, it has 8 valence electrons. If it's in the 1st column, it has 1 valence electron. If it's in the 7th column, it has 7 valence electrons. You can guess the 2nd column has 2 valence electrons. In the 3rd column, that's the one with boron in it, that has 3. The 4th column, that's the one with carbon in it, that has 4 valence electrons. The 5th column, which has nitrogen in it, that has 5 valence electrons. 6th column, which has oxygen in it, that has 6th column, which has oxygen in it, has 6 valence electrons, and it goes across like this. And so by identifying what column they're in, you can figure out how many valence electrons. Potassium, that's in the 1st column, so it has 1 valence electrons. Magnesium is in the 2nd column, it has 2. Nitrogen is in the 5th column, it has 5. Helium is weird, okay? Helium is in that 8th column, but it's a special exception because the only thing in that row with helium is hydrogen. And so since it's only the 2nd thing in the row, it has 2 valence electrons. So helium is the only thing that breaks this rule of valence electrons where it doesn't match up with its column, but everything else does. So remember, helium has 2. Fluorine in the 7th column, it has 7. Argon, with the noble gases being in the 8th column there, it has 8. So talking here, this actually, I think that's the same thing for some reason twice in a row. All right. So here's why valence electrons are important. So they're involved in the bonding. Bonding is usually sharing or giving electrons between things, and so how many valence electrons something has really matters. And then this is something that's called the octet rule. So atoms really, really want to have 8 valence electrons. They want to have that because that's what the noble gases have, and the noble gases are especially stable, and so they want to be like noble gases. So they're going to either lose electrons or gain electrons, whichever is easiest to try and become like a noble gas. All right, and then remember, if we're losing electrons or we're gaining electrons, we become ions. Ions are charged atoms, all right, and so, but when it takes on that ionic state, it's going to be like a noble gas. It's going to have the same number of electrons, which makes it stabler than it would be in its neutral form. And so we're going to look here and we're going to see what charges we think things will take on. If you look at potassium, potassium is in the 1st column, so it has 1 valence electron. If it wants to be like a noble gas, its choices are to lose 1 electron, and then it's like argon, or it can gain 7 electrons and be like krypton. Losing 1 electron is easier than gaining 7, and so it's going to take on a +1 charge and lose that 1 electron. If it loses an electron, electrons are negatively charged, so losing an electron gives you a positive charge. Magnesium is in the 2nd column. That means its choices are losing 2 electrons or gaining 6. It's going to lose 2 electrons because losing 2 electrons is easier than gaining 6. Nitrogen has 5 valence electrons, so it can either lose 5 or gain 3. It's going to gain 3 electrons, which means it has a negative charge, -3. Helium is a noble gas, so helium is not going to want to gain or lose electrons. Fluorine has 7 valence electrons, so it's going to want to gain 1 more electron, so it has 8. That's easier than losing 7. And then argon is a noble gas, so again, it's not going to react. And then these are the noble gases that they're like. So what we're saying here is magnesium, when it gives up those 2 electrons, it becomes like neon. Nitrogen, when it gains its 3 electrons, it becomes like neon. Fluorine, when it gains its 1 electron, it becomes like neon. But becoming like a noble gas in your electron configuration makes you more stable. And so that's why they do that. So that's a general introduction into valence electrons. And as I said, it's important because that helps us understand some of these periodic trends. So going back here to what we were talking about, way back here with the ionization energy, I said that as you go across a period, ionization energy, again, remember, is the amount of energy it takes to remove an electron. As you're going across a period, that means as you're getting closer and closer to the left side of the periodic, or the right side of the periodic table, you're getting close to the halogens and the noble gas. It becomes harder to give up electrons as you're closer to the noble gases because you're closer to having that octet. And so really, ones that are on the right side of the periodic table want to gain electrons, and so they won't be giving them up. So generally speaking, is going higher and higher. And here, the noble gases really don't want to give up their electrons because they're noble gases, which makes them especially stable. So they're not going to want to give those up at all. So comparing ionization energies here, strontium or iodine. Iodine is to the left. It's very close to being xenon, all right, which is a noble gas. So iodine wants to gain 1 more electron. It definitely doesn't want you to take 1 away, all right? And remember, ionization energy is the amount of energy to remove an electron. And then strontium here, strontium is actually kind of fine if you take its electrons because if you take a couple electrons away from strontium, strontium becomes like krypton. So iodine is going to put up a larger fight if you try and remove electrons from it. So the one that has the higher ionization energy is going to be iodine in this case because it's close to xenon. It wants to gain 1 electron, not lose an electron. So iodine has a higher ionization energy. For these two, potassium and bromine, same concept here. Potassium actually kind of wants you to take its electron because then it's like argon. Bromine wants 1 more electron to become like krypton, so bromine is going to put up a larger fight here. So ionization energy, the energy required to remove an electron from these, bromine is a lot harder to remove an electron from than potassium is because bromine is almost krypton, and it really doesn't want you to take its electrons away. Potassium, on the other hand, if you take an electron away from potassium, it becomes argon, so it kind of likes it if you do that. So that's how that works. Oxygen and selenium here. The one with the higher ionization energy is oxygen. Remember, oxygen, it's a smaller atom. It has less shielding, and so as you get closer and closer to the nucleus here, it's harder to take electrons away. Selenium is much larger, so you can kind of just go in and grab an electron off of selenium, and it's such a big atom that it doesn't put up much of a fight. But oxygen is only on the 2nd energy level there, so removing an electron from oxygen is actually pretty hard because the electrons are so close to the nucleus, relatively speaking. Okay, now we're going to talk about something called electronegativity. This is similar in a lot of ways to the ionization energy, but you need to know the difference. And so electronegativity has to do with the way that an atom might pull an electron or unequally share or hog an electron from another neighboring atom. And so this all has to do with when 2 atoms kind of come near each other, its tendency to steal or hog an electron from something else. So generally speaking here, if we're talking about this trend as you go down the group, again, it's kind of similar to the ionization energy here. If you're going down a group, its ability to grab or steal an electron from something else is going to get smaller because it's further away from the nucleus. And so if electronegativity is something's ability to grab an electron from another atom, if you've got a big atom, it's going to be harder for it to grab and hold on to something else's electron. So that's the idea there. As you go across the period for electronegativity, this one, similar with the octets. If you're getting closer to an octet, you really are grabbing at other people's electrons because you want those electrons so you can be like a noble gas, all right? If you are something that is on the left side of the periodic table, you don't want to grab at the electrons so much because you're not close. In fact, you want to lose electrons if you're on the left side of the periodic table. And so this is the general trend here. One way that this really, really differs from the ionization energy is that the noble gases actually they have 0 for their electronegativity. So the noble gases are actually the lowest thing on the periodic table in terms of the electronegativity because they don't want to gain or lose electrons. Noble gases are good how they are. And so if electronegativity is a substance's tendency to like steal electrons from something else, well, a noble gas isn't going to steal electrons from anything else because it's already good the way it is. So noble gases have 0 for their electronegativity. For the ionization energy, remember that the noble gases were really, really high because the ionization energy is the amount of energy it takes to remove an electron from an element. It takes a lot of energy to remove an electron from a noble gas because noble gases are very stable. They really don't want you to remove that electron. So ionization energy for noble gases is really high. But the electronegativity for noble gases, that is the noble gases' tendency to grab electrons from other things, that's actually very low, right? Because noble gases don't want to grab the electrons from other things. And so, I don't know, it's a little bit confusing, but hopefully you understand the distinction there. Both of them have the same general trend that electronegativity and ionization energy are getting larger as you go up and to the right. However, the main difference there is that electronegativity is 0 for the noble gases, whereas the ionization energy is really, really high for the noble gases. So going and comparing these, as we saw here, we're going to do selenium and bromine. Bromine is further to the right, which means it's closer to being a noble gas, which means bromine is actually going to be more likely to steal an electron from something else, because if bromine steals an electron, it becomes like krypton. So bromine is really, really likely to want to steal an electron from something else. Looking at francium versus cesium. Francium here, lower on the periodic table, cesium higher on the periodic table. And so cesium, because it's a smaller atom, because we're talking about things that are closer to the nucleus, cesium is better able to grab and hold on to elements from electrons from other elements because it's a small thing relative to francium. Francium is really, really large, so all the electrons are on the outside. It's really hard for francium to grab and hold on to electrons from other elements. All right, and then chlorine and bromine, similar rule. Chlorine has a higher electronegativity because chlorine is smaller, which means it's better able to grab onto electrons from other things. For bromine, it has an extra energy level there, which means it's got more atoms, which means it's harder, or more electrons, sorry, which means it's harder for it to grab on to something new. So that's the deal there. All right, so now we're back to valence electrons, and I've already actually gone through this part of the slideshow. So try and remember those different trends, especially like look back and try and make sure you understand the difference between ionization energy and electronegativity, because that's probably the most confusing thing in this PowerPoint. And of course, if you have any questions over any of this, make sure you come in and ask.